Hi Paul, it's a pleasure to see you again. Today we are going to cover the geometric Brownian motion process in a slightly different way. We are going to show how the GBM stochastic differential equation arises as a generalization of the calculations we encounter on almost a daily basis, and we are then going to solve this SDE. Let's consider the population of a country. Let's say it grows at a constant rate R per unit of time, where we will take the unit of time to be 1 year. So if the population starts at x0, then by the end of the first year, it will grow to x0 times 1 plus r. To get the population at the end of the second year, you will multiply it by 1 plus r again, and so on. So if we want to know the population after t units of time, which is t years, then we take the initial population and multiply it by 1 plus r t times. X and t here are discrete variables, but we are going to turn them into continuous variables. Now instead of the human population, let's consider the population of bacteria. We want more dense population so that we can pretend we are talking about continuous variables. Now assume instead of 1, we have f compounding per unit time, and the rate is still represented in terms of our unit of time, so it is a yearly rate. So in each compounding period, the population grows by r divided by f, and as there are f periods per year, there will be f times t periods and t years. So in comparison to the previous formula, you are replacing r by r divided by f and t by f times t. For example, if the compounding is quarterly, then the per quarter growth rate will be r divided by 4, and the number of quarters in t years will be 4 times t. So the population after t years will be given by this formula. Now let the number of compounding periods per unit time goes to infinity and beyond. And we know that this limit, ignoring the t in the power, is just one of the definitions of the exponential function that Euler came up with in the 18th century. This is the same guy who invented a lot of the symbols that we use today, by the way, such as f of x for function of x, pi, delta x, etc. So if you don't like any of these symbols, then you know your guy. But he's probably most well known for the Euler identity. And we also need the composition law of limits because we have the extra t and the power. So we get. And we also know from the properties of the exponential function that e to the power r to the power t is just equal to e to the power r times t. This can be easily viewed as multiplying e to the power r t times, and then noting that multiplying exponential functions amount to adding the terms in the exponent. We know Euler was brilliant, but you don't have to trust him without verifying, so let's see whether this approximation makes sense. Let's plot the function e to the power r. You would have seen this function written in terms of x, so think of r as x if that helps. Now let's plot the approximation. We start with f equal to 1, so we have 1 compounding per unit time. So the approximation is not great, but it improves as we increase f to 2. Now if we let f increase, then you can see the approximation approaches e to the power r. For f equal to just 24, we are getting quite good convergence, so we have no option but to believe the guy. We are going to interpret everything as continuous variables now. Now, if you want to know the population at t plus h, with h being a small time interval, then we just replace t by t plus h. And we can now calculate how the population changes per unit time over an infinitesimal period. We can substitute the expression for xt plus h and xt to get. So the numerator is the change in the population over the period h, and denominator is the length of the interval over which we are calculating the change, and we are assuming this h is very small, and we know this is the definition of derivative. Now on the right hand side, we can factor out the common term, which is x0 times exponential of rt. Now let's recall the series expansion of e to the power x. This is just Taylor series approximations of e to the power x around 0, by the way. To see, let's recall the Taylor series expansion of a function f around x. Now our function is e to the power x, and all its derivatives are also equal to e to the power x. So this becomes, now set x equal to 0 and you get the series expansion of e to the power x. By the way, this x should be interpreted in the delta x sense, this small change around 0. So for a given number of terms, the approximation will be more accurate for smaller values of x, but our r is supposed to be small as it is the growth rate, which is usually small, and h is supposed to be very small. So ignoring terms higher than the second order will be fine here. By the way, you can derive this expansion using the limiting characterization of e to the power x that we saw before. You just need to apply the binomial expansion of the x plus y to the power n, which is as follows. So this is a more general version of the famous x plus y squared formula, as you can easily verify. Now if you apply this to our expression, then after a little simplification you will get. And now if you take the limit as n tends to infinity, you get the series representation. So everything suggests the same thing. Now we can apply this to the e to the power r times h. So we get, now we cancel 1s and get rid of the h in the denominator by dividing the terms in the numerator by h. Now as h tends to 0, the term that contains multiplication by h will also go to 0, and we can substitute xt for x0 times the exponential. And if you like the life on the fast lane and don't have time for the first principles, then you can get this differential equation by just applying the derivative rules that you would have been forced to memorize at some point. So you can take derivative with respect to t, where we took the x0 term that doesn't depend on t out of the derivative. Now we know the derivative of e to the power t is equal to itself, and we need to use chain rules because the term in the exponent contains r times t, and we know x0 times e to the power rt equals xt, so we get the same result but faster. So we get the differential equation that produces this process. Solving this equation subject to x0 will give us the solution. You can also write this in the fancy differential form by shifting dt to the right hand side. Now you can use this same equation to model many phenomena. For example, instead of the population, you can interpret x as the balance of your bank account. Hope you did manage to save some money, and r as the interest rate. You can also model radioactive decay by setting r equal to a negative value, so minus r for decay and positive r for growth. Now the growth or decay rate doesn't have to be a constant. For example, in certain situations it could be a function of time. Here we are assuming it is a deterministic function of time, but some other situations might demand the growth rate to have a random component. So this dRt describes the random changes in the growth rate. For example, when you deposit the money with the bank, you know at the beginning of the period what rate you would get, ignoring the possibility of the bank default. Now the interest rate that the bank pays you will vary over time, so there's a use case for the time-dependent R. Now assume you invest money in a stock by buying shares of a company. You expect to earn a return, but now the return depends on the future price of the stock. So this is a use case for the need to have a random component. The random component will be a stochastic process, and there are many types of stochastic processes that one can use, but as the name implies, in geometric Brownian, one assumes the random changes to be given by the Brownian motion process. Now the standard Brownian motion increments over an interval are normally distributed with mean equal to 0 and variance equal to the length of the interval. You may want to scale the contribution of this process by multiplying it by sigma, and now you can get a more general version with which you can model processes exhibiting different levels of randomness, and the deterministic growth rate term allows you to control the mean. Whilst the r and sigma can be functions of time, we will assume that they are constant, and let's also get rid of the brackets. Making them function of t doesn't make a huge difference, but the presentation will be much easier if we assume they are constant. So in the deterministic case, the infinitesimal changes were given by the differential equation, which is non-random, and hence the mean is given by the same right-hand side, and the variance is 0 because the variance of a deterministic function is 0. And the stochastic version, the infinitesimal changes are given by the GBM SDE, which is random because of the presence of this Brownian motion. Now when we are at time t, our assumption is that we will know the value of the process xt given the information that is available to us at time t. So we can calculate the expected value conditional on the information that is available to us at that time. As the mean of the Brownian increments is 0, the mean of the infinitesimal changes is just r times x times dt. F here represents the filtration, which you can interpret as the information available to us at time t. For the variance, we know the variance of the deterministic component is 0, and the variance of a scalar times a random variable is equal to the square of the scalar times the variance of the random variable. And we also know the variance of the Brownian increments is equal to the length of the interval. So we get, so the infinitesimal changes are not deterministic anymore, and they have a probability distribution. By the way, the mean and variance here refer to the mean and variance of the infinitesimal changes as opposed to the mean and variance of the process, which we will cover later on in another video. Now this variance is the probability weighted average of the displacement squared, but the quadratic variation of the process, which is like limiting sum of the squares of the displacements when the interval is divided into a large number of subintervals, is also equal to this expression. And it's easy to see that for the standard Brownian increments, this means dB squared equals dt. Remember, variance of dB is dt, so you can see the analogy. Now dt is supposed to be very small, so we can ignore the higher order terms such as dt squared and dt times dB. And by the way, you can get the previous expression for dx squared by applying a plus b squared formula to the dx, and then setting the cross in higher order terms equal to 0. Now we are going to proceed to solve this SDE. Let's first consider how could one solve the deterministic version of the differential equation. We know the solution, but let's pretend we have been asked to solve this differential equation. Now this is a basic differential equation. One naturally tries to separate the variables, so we shift x to the left-hand side. Now the left-hand side is just the differential of log of x. We just need to integrate and exponentiate, and we will get the solution that we already know. Now we can try the log of x for determining the solution of the stochastic version as well. Now we are in stochastic world, so we need Ito's lemma, which is just first derivative times dx plus half the second derivative times dx squared. We know derivative of log of x is equal to 1 divided by x, and the derivative of 1 divided by x is equal to minus 1 divided by x squared. Now we can substitute for dx and dx squared, so the x's cancel, and we can combine the dt terms. Now we integrate, assuming we are interested in the solution at capital T. The differential and the integral on the left-hand side cancel, and taking the constants out of the integrals on the right-hand side. Now we can write the log difference as the log of the ratio on the left-hand side and evaluate the integral on the right-hand side. Notice B naught is 0 because Brownian motion starts at 0 by definition. Now we need to exponentiate both sides, and noting that the exponential and log are inverse of each other, we get. Now we just need to shift x naught to the right hand side and we have the solution. We can also take the x naught upstairs if you like. This makes the probabilistic interpretation easier, as we can see now that xt is like the exponential of a normal random variable. We know that if y is normal with mean mu and variance sigma squared, then the exponential of y is log normal. In our case, determine the exponent is normal, whose mean and variance are as follows. The mean is just the deterministic part and the variance is just the square of the coefficients of Brownian times t. So we can say our x is log normal with the same parameters because its log is normal, right? Now we can easily generate the distribution of the log normal. So we can determine the distribution of the process x or a function of the process x at any horizon. However, in some situations we will be dealing with functions that depend on the paths of the process, but there's no problem as we can also construct the paths of the process. Let's see one way one can go about it. We know that the value of the Brownian is normally distributed with mean 0 and variance equal to the length of the interval. So we can represent the Brownian as square root of t times a standard normal because it also has 0 mean and variance equal to t. Remember, applying variance to a scalar times the random variable produces the square of the scalar times the variance of the random variable. Now we can substitute this expression for bt. By the way, we can also generalize this process to an arbitrary starting point, t as opposed to 0. All one has to do is to replace 0 by t and big T by t minus small t. And we can also write this in terms of delta t as in size of the time step. So you just replace the difference of time by the length of the interval, which we represent as delta t. And we can also write its distribution easily by just replacing t by delta t. Now let's see a quick example. Assume we are given the following parameters. The distribution and the solution have this r minus sigma squared term. So let's calculate it here. We just substitute the numbers and then evaluate the expression. Making the substitutions into the solutions and the distribution equations, we get. By the way, this correction to the drift and the distribution and the solution is a constant source of confusion in the beginning, but it eventually starts to make sense. Now we can easily simulate the paths of this process and also the distribution of the process. Assume the current value of the process is 1, and for the paths, assume we are simulating the paths with a time step of 0.05 years. If you assume 360 days in a year, then that would be like observing the process every 18 days. That's like 20 working days a year. Ideal job it would be one day. So to simulate the paths, we take the current value as xt in this equation, generate a standard normal variable, and plug the z and the delta t in this equation, and we get the simulated price at the next time step, which is x 0.05. We then use this value as the new base, generate another standard normal, and generate the value at the next time step, which is x 0.1, and so on. We can then simulate another path, and so on. If you generate a large number of paths and then say, look at the terminal values of these paths, you will get a log normal distribution. So if you're just interested in the distribution at a given time, then you can just generate the distribution using the analytical formula for the log normal density, which is similar to the normal density, but you have the log of x in the exponent, and you have 1 divided by x at the front as well. Now you can actually generate the distribution surface, which is the distribution of the process values over time. For given mean and variance, the density formula is a function of t and x, so it is just plotting a function of two variables. By the way, even though we have a nice surface, this surface still represents the one-dimensional distribution, so this is not going to work for path-dependent functions because you will need to know the joint distribution of the value at multiple times. From the surface, we can tell that the distribution starts at the current value because the current value of the process is known, so probability is concentrated at the current value. As time progresses, the distribution spreads. This is like a continuous version of the one-dimensional terminal distribution we saw before, by the way. For example, slicing the very end of this surface will produce the distribution of the terminal values plot that we saw before. So what it is saying is that the terminal distribution will be wide and flat. This is because the variance grows with time, right? Remember, sigma squared times t. And as one approaches today, the distribution becomes concentrated. And let's see it in the natural direction once again before we say goodbye. So we hope you enjoyed the video and we look forward to seeing you in the next.